Now that we have talked about EMFs induced in coils through which a magnetic flux is changing, and we've talked about a simple example of motional EMF, our example where the rail was moving along a set of fixed rails, we can talk about this rotational EMF. So we've seen in the examples of electric motors that if I have a coil of wire that looks something like this, and I run a current through this coil, and this coil is embedded in a magnetic field, the coil will feel a torque and begin to rotate. And so if I take this system and I put in a current, what I get out of it is some motion. And I've given this angular velocity omega here. So I put in a current and I get out rotational motion. Fair enough. What if I don't put in a current though, and I put in rotational motion? In other words, what if I force this coil to turn somehow? Maybe I attach it to a crank and I just crank it with my hand. Maybe I hook it up to an internal combustion engine and make it turn that way. Maybe I attach it to a spinning wheel and make a hamster run in it. However I choose to do it, if I make this thing rotate, what happens? Well, we now have the physics to answer that question. There is a flux through this coil that will change in time, right? This is a radians per second. This angular velocity necessarily occurs in time. And so if this is rotating, the flux through this coil is changing in time. And so I get an induced EMF in the coil, which then causes current to run. Congratulations, you've made a generator. And so what is the difference between a generator and a motor? Well, conceptually speaking, not a whole lot. For a motor, an electric motor, I put in current in, motion out. For a generator, I put in motion and I get current out. In other words, if I make current run through the loop, the loop will rotate if it's free to do so. If I make the loop rotate, then current will flow as long as the circuit's closed. So it looks to me that a motor and a generator are really two sides of the same coin, and that makes some sense. We're going to see in the next section that even when you have a motor, the motor will act like a generator. We'll save that for the next section, but they're very, very, very similar. Conceptually, if I were to draw the diagram, if I were to draw this diagram and ask you, well, which is this, a motor or a generator, especially if I had already put a current in there, you really couldn't tell. You'd have to ask the question, well, what came first, the current or the motion? Because if the current comes first, then the motion follows, and we call that a motor. If the motion comes first, the current follows, and then we call that a generator. No big deal. All right, so how do we characterize that? Without going through the derivation of this equation, the real derivation of this equation is going to take some calculus. If you're in my course, my 1510 course, your book goes through, if we're still using OpenStax when you're watching this video, your book goes through kind of a derivation. I'm not a huge fan of the derivation, so I'm going to leave it. But I'm going to write down the equation and talk about what it means though. So the EMF induced in this coil, if I make this thing rotate, so I've been comparing motors and generators. I'm really talking about generators now. So I'm going to make this thing turn. I'm going to put in motion. I'm going to get out a current. So the equation that will describe that is this. Make sure that's all in frame. It is. The EMF induced in this coil can be given by this expression, where N, as always, is the number of turns, or the number of loops, however you want to say it. As I've drawn it, there's only one loop, but there's nothing, of course, to prevent me from wrapping this around and around and around. It's an easy way to increase the EMF. If I take off this N, or if N is equal to 1, this is the EMF induced in just one turn. But if I have more than one turn, then I put out every number of turns I have in there. A, this is the area of the loop. B, of course, is the magnetic field. Omega is the angular velocity. And then the sine omega t. Notice omega t. Let's just look at that expression. Omega has units, so I'm going to write it omega t. By units, this has radians per second times a second. What I'm going to get out of that is just theta, right? Where theta is an angle measured in radians. If from the units, I get out radians. What that means is that this quantity, omega t, has got to be just be an angle. And that's what's going on here. As this thing rotates around, it describes different angles. We start out at some point, let's call it 0, and then a certain amount of time t later, as it's rotating at this velocity, we've subtended an angle of theta, right? And theta could run from 0 to 7 billion pi. We just keep going and going and going. Of course, we can always reduce that to an angle between 0 and 2 pi. But of course, the angle between these two has to determine the EMF, because that is critical to determining the direction of the forces here. And remember, not the direction of the forces, the direction of the velocity of the sides of this coil. And the velocity, remember from our discussion of motional EMF, the velocity makes a difference to the force. So in this case, the angular velocity is going to make a difference. The sine omega t is going to give you the specific angle at which this thing is when you look at the system, right? So this component out in front is sometimes called, let me circle that in a different color. This component out in front is sometimes called E naught. It's just a simplification to enable us to write this equation as this. I'll write it down here. E at any time is equal to E naught sine omega t. Both of these mean the same thing. I'm probably never going to write this. I'm going to write this because I think it's handier to have it sitting out in front of you. But this is the equation that gives you the induced current, the induced EMF at any particular time in the coil. Now, as it turns out, that's not particularly useful for practical applications because this is the instantaneous EMF. This is different at every point in time. We don't want that. We don't want our EMFs to fluctuate. And if, in point of fact, if you have a generator producing an EMF and you measure the EMF across the terminals of the generator, it doesn't fluctuate that much. Omega is so fast that what you get in real life is an averaging out of all the peaks and valleys. Right? This is a sine function. If I graphed this function, it would follow a sine curve. And there's nothing wrong with that. But what I really need out of a generator is a constant voltage, which this will give me in the average. So this is the equation that talks about the instantaneous EMF. Let me show you the average EMF. If I take the equation we just had, and I average this over one period, well, if you remember from trigonometry, the average of a sine function over one period just gives you 1/2. On the average, I'm going to get 1/2 out of this. So that tells me that the E average is equal to NAB omega over 2. So whichever one of those you need, you can use whichever one. Sometimes people will ask you for the peak voltage. The peak will occur when your trig function here is maximized. The maximum value of sine is going to be 1. So your peak voltage is just NAB omega. Your average will be that over 2. Your minimum voltage, of course, it depends on who's asking the question. Some people would say that it's 0 because sine goes down to 0. But remember, the minimum of sine is actually not 0, it's -1. So your minimum voltage could be negative NAV omega. That would be a strange way to talk about it. Normally we look at the magnitude of this, not the sign. But if somebody asks you for the minimum EMF, I think it's appropriate to say, do you want the minimum by magnitude, which would be 0, or the true minimum, which would be negative NAV omega. But at any rate, these are the equations that are going to describe the EMF induced in a generator in a turning coil of wire.